Okie dokie. Hey, we are just about to get started here. So welcome in, guys. It's week 6 now, right? Week 6. Yeah, week 6. This week we are covering decision trees, which don't let the name really spook you. They're not that complicated. More or less, we'll get into this in a second. They're just really long if-else statements, and we'll cover why and how they're useful in a bit more detail. But that's more or less the gist. So if you wanted just that, then you're free to go. But otherwise, we'll get into a bit more interesting stuff right now. So this is more or less our agenda for what we're covering today. Sorry, this is frozen still. Uh, there we go. So our agenda for today. First thing we're going to talk about is the importance of interpretability, or how you can understand what a model does. Going into just general, what does an if-else statement mean? How to explore this with nested conditional statements. So just an if-else going into another if-else. How to build a decision tree and what a random forest means. And we'll get into all that. And at the end of this, you'll do some coding as well. But we'll get there. It's going to be fun. So the first thing that's important for us to cover in order to get a general idea of why decision trees are important, why they matter for us in this field generally, is the concept of interpretability. So the idea generally of interpretability is being able to understand why a decision is made. So think if, for example, you're in court and a judge makes a decision seemingly at random after just reading the facts of the case without any actual trial where you could actually build reasoning for why something's happening, but instead just makes a decision seemingly at random. So interpretability in these cases is very important. And with a lot of other machine learning models, as we'll shortly get into, there isn't any. So quickly, on this scale from completely non-interpretable to extremely interpretable, just things that we can tell how they work and why, we have a few examples here. So something that is completely non-interpretable is what is considered a black box. A black box in machine learning, or in general, is something that has a defined input and a defined output, but we don't know what goes on in the middle. So we don't have any idea about the structures, how the decision gets made, how the information gets processed, nothing. We just know that there's some input and some output. This is inherently non-interpretable because we don't know how the decision is being made whatsoever. We just know that there is a decision. This isn't very useful if you're trying to figure out why your model does something. Slightly more interpretable is something like a deep neural network. A deep neural network, you can see the input layer and you know the architecture of the network, but you don't really understand how the math happens really, or why decisions get made. It's just interactions between different nodes within the network, and then a decision gets spat out at the end based off some input that you give it and after some thinking time. So again, not very interpretable. You don't know why things are happening. And these are a lot of problems that occur with contemporary, exceedingly large machine learning models. Quickly, can anyone think of an example of a machine learning model that you might have used where you don't really understand why it's doing something? This can be anything. Yeah. ResNet? Like, explain for everyone what that might mean. Yeah, so ResNet, for those of you who don't know, is a machine learning framework that you can use for a variety of different purposes, like our friend over there mentioned, for transfer learning, which is taking the weights of one model and using it for a different task. It died. I'm going to keep talking because I think you guys can hear me. Please fix the batteries. And taking that and transferring it over to some other task. Inherently, you don't know why it does this. It's the exact same problem as the deep neural network. And there's a lot of issues with this. We don't have any idea of what's going on. So this is an example of something that is inherently non-interpretable. Going forward is something like linear regression here, where we can see that there's data here, and we draw some sort of decision line between it, and that allows us to make a decision and know why the decision is being made. So we have class A and class B, and we can see where the linear separation is and intuit why the model did that. So we have actual decision, and we know why the decision was made in that specific way. Unlike this, where we just have a general idea of the innards or no idea of why something's happening whatsoever. And at the end of something like that's the most interpretable, we have something like an if-else statement, where we know the input, the output, and the decision rule. So like if the sky is blue, say yippee, and otherwise say boo, is very interpretable. You know exactly why it's doing something. You know the logic. Thank you very much. And you know the reasoning for how everything else is happening. So this is the scale. Decision trees fall comfortably on the end of interpretability. And we'll get there in the second why. So consider this simple example, right? If we're looking at college admissions, for example, a very simple determining factor for why someone gets into college might be their GPA. So if they have a good GPA, then they're admitted, and if they have a bad one, then they're not admitted because their grades suck, right? So what happens if we want to string these together and make something a bit more complicated? So the first thing we do, just to structure it similarly to how you might see decision trees normally, is just turning it on its side. You'll see why it's called a tree in a moment, I think, but it's effectively the same. What we call here at the top is our root node. This is just the base of our tree. Think of it like where the tree is at the ground before you have roots. The main trunk before you go into branches at the top. And we continue down. We add a few more determining factors. So instead of just immediately accepting people with a good GPA, we ask, okay, but do they have a good SAT score as well? And if they do, then they're accepted. Great. And if they don't, then we get rid of them because they're not as important to us, right? And it can get even more complicated. So we can check if someone doesn't have good grades, whether or not they have good extracurriculars. And if they're really good at extracurriculars, then we accept them. If they don't, we get rid of them, et cetera, et cetera. And you can keep going until you have something really complicated like this. And if you want to read this, as an article from Journal Nature with some details about a similar sort of application to, I think, public records for this type of stuff. And this is the type of thing we'll be talking about today. Literally just how to make these larger decision trees and make decisions along these lines that are viewable, where you can see how decisions were made with those rules available. So considering our table here, our college admissions table, let's go through a few examples. So John here has a good GPA, a good SAT, but bad extracurriculars, but he was the MVP of his sports team and he was never suspended. So let's walk through the tree real quick, yeah? So starting at the top, let me turn this on, let's do this. Starting at the top. So John has a good GPA, yeah? Which way are we gonna go? Are we gonna go true or false? You can call out, this isn't really anything serious. Yeah, okay, great, true. He has a good GPA, amazing. So from here, does he have a good SAT? Yes or no? I see nods. Yes, he has a good SAT. Has he ever been suspended? No, he has not. Great. So that means that, wait a minute. Good GPA, good SAT. Oh, he hasn't ever been suspended. Amazing. Wait, no, good SAT. Yeah, he hasn't been. Oh, perfect. He's been admitted. I just can't read the table. That's awesome. And just like that, we can see that he was admitted following the same logic. Same thing for Joe. He has a bad GPA, so we're going to go here. He's false. He has good extracurriculars. And he was not the MVP on his sports team, which means that he is unfortunately rejected from our hypothetical educational institution. And then for James, same thing, good GPA, bad SAT. So he's just rejected outright, if I'm not mistaken. Perfect. So that's the basic idea of a decision tree. What we're going to do is come up with rules based off of our original data and come up with decisions based off of that. And that is the beginning and end of the complexity of this. Where it becomes more complicated is figuring out why you want to make these decisions, where you draw the lines for what these rules should be, because we can't tell the computer how to do that, and how we come up with this so far. Before I get into that, does anyone have any questions on this? Just the basis of what a decision tree is. Great. Keep going. All right. So this bit's going to be a little bit complicated, but I think you guys will get a decent handle on it, hopefully. So this is the concept where this is a very important concept in training trees called information gain and information entropy. Both of these are a little bit complicated, and I'll try and go slow so we can get a general understanding of how they work. But feel free to stop me at any time if you have any questions, because this is the teensy bit mathy. So we'll get into it real quick. So entropy, not to be confused with the actual physical process, is just a way to measure how noisy a piece of data is. If you look at the graph in the top right of this slide here, you can see that the peak entropy when comparing two variables is at 0.5. That's the probability for outcome A. Let's say you have, for a college admissions example, whether or not someone got into a school or whether or not someone was rejected from a school. If those are equally likely, then you're going to have an entropy of 1 because you cannot distinguish between them. It is the most noisy that it could possibly be. But if every single person gets in, like 100% of the time you're getting into the school, the entropy is 0. There is no noise in your data set because it doesn't matter, in essence, what the result is. You are always getting in. So it's a bell curve where both ends are 0 because it doesn't matter. You don't need to know the other piece of data. and it's the most noisy, and entropy is 1 when each one is equally likely. Yeah, that's a good example. So if we're considering our college admissions table here, high entropy would be, for example, right here, where 11 people are accepted and 9 were rejected. And we'll go into a little calculation on the next slide as well for how this would look. Perfect. Oh, never mind. On the same slide. So single attribute entropy. This is going to be a little complicated and slightly mathy. Forgive me, but it's not that bad. This is our main equation here. The entropy is the sum for each term. So each term here, I believe that's, yeah. So for whether or not someone was accepted, rejected, etc., times the -1 times the probability of that term occurring times the log base 2 of that probability. The reason that we do log base 2 is because we're trying to represent entropy as a bit value. Originally, this was developed as a way to store this information digitally. So the actual outputted value from doing log base 2 of a probability is going to give us the actual size of value that we need to store, how many possible event spaces we have. So that's not super important, but basically the calculation goes, if you can see right underneath there, we're going to take our value here, 9 out of 20, so the amount of times people were rejected, times the log base 2 of 9 out of 20, and then the same thing for the amount of people who were accepted. And the entropy result from this is that it's very, very close to 1, like 0.993, which just means that we're very, very close to 50-50. So our data for whether or not people are accepted or rejected is very, very noisy. Now, this isn't particularly useful for us just being able to classify outright. We can't look at this table and make a decision just very easily as a computer. So we need to do something to transform our data a little bit. And that'll also help us split our data by using a decision tree. So before we get into that, quickly, who can tell me which one of these containers of marbles has a higher entropy? Remember, entropy is a measure of noise. So whichever one is a bit more noisy. Like if you were to stick your hand into one of these bags, which marble would you get out, more likely or not? In the back there, yeah. Yeah, exactly. Because red and blue are more similar in probability, this one has a higher entropy. That's the whole thing. Great job. Okay, let's keep going. So multi-attribute entropy. This is a little bit more complicated, but we'll get there in a second. So for single attribute, we just covered this. Multi-attribute, what we're basically going to be doing is multiplying the probabilities together. So here, the entropy of getting accepted with high GPA, I think. Yes. Sorry. Yeah, that's correct. So we take our initial cases. This person. So if we compare good GPA, which is 12 out of the 20, this is the expected value of doing just 10. I think it's like 10 over 12 times log base 2 of 12 and 2 over 12 log base 2 of 12 combined gives you roughly 0.65. And then doing the same for bad GPA, combining those together, we get roughly 0.61. Slightly complicated. And I know I kind of ran through this a little bit quickly, but more or less the idea is you're combining the likelihood, the entropy of the individual property by the probability of the new one. So because we're looking here, we know the entropy of getting a, let's see, what was it originally? It was, yes, it was based off of GPA. So we're comparing good GPA versus bad GPA. Then we're comparing the percentage of acceptance, I think. Yes? Your cone got this.
The way that this part works with multi-attribute. Data. Bad GPA, how that affects their acceptance. We look at the first format.
Yep. Yeah, his explanation is going to be better than mine. He knows this a lot better than I do. But for the sake of argument, let's say that this is how this works. So from here, we need to cover the main important thing for how we make decision trees called information gain. More or less what we're trying to do is compare the distribution of our data based off of a rule that we come up with. So let's say that we're going to be splitting our data based off of whether or not people get in based on good GPA versus bad GPA. As we can see here, people with good GPA tend to get accepted a lot more than people with bad GPA. So it's a very good way to discriminate our data and come up with a decision. So the goal of a decision tree, in essence, is a way to split our data into definable outcomes. So we can take all of our data, lump it together, and then say, okay, if this person has a good GPA, then we're going to probably accept them. And if they have a bad GPA, we're probably not going to accept them. And we can add more splits as we make the tree more complicated. Information gain is the way to basically come up with this. So what we're going to be doing is comparing the original entropy of getting accepted to the school with the new one conditioned on the GPA. So if someone has a high GPA, for instance, they're going to be more likely to be accepted. And this number here, the 0.38 that I'm circling with my hand there, is a way to represent numerically a way for us to split our data. So we know that this is going to be very, very useful as a way to minimize the noise in our data. Everyone with me so far? Roughly. This isn't the most important thing, but in terms of theory, if you want to make a decision tree, the way to do it is to minimize entropy. So make the data more cleanly discernible based on each step that you do. Any questions real quick about entropy, information gain? Yeah. It's a question of being able to split it cleanly. So if, for example, we have, here, actually, there's a pen over there. Oh, go to the next slide, and that might explain it, but also draw something. Yeah, so if we have, yeah, actually, this works great. So if we look at the two slides here, or the two sides of the thing here, we take our original distribution of data, they're identical, and we split them. The first one into this, and the second one into this, and the first one into this, and the second one into this. Which one do we think is more effective as a split? Just cleanly. If, for example, blue is accept and red is reject. In the back. One of you, it doesn't particularly matter. Sorry? The one on the right. Can you explain why? Exactly. So if the goal is prediction, we're going to get a much better chance predicting that anyone in this bag is going to be rejected and anyone in this bag is going to be accepted. Every step in the decision tree should get us closer to actually predicting what we're looking for. So whether or not it's college acceptance or if someone is potentially guilty of a crime, it doesn't matter. This is the type of information that we're looking to maximize. So making the separation as clean as possible, every step of the decision tree should be maximizing that information gain. Make sense? Cool beans. Any other questions?
It's very complicated.
Perfect. Okay. So let's consider college admissions once again, yes? In this case, with several different attributes, we want to make a decision tree with this type of information. So how do we choose which attributes we want to maximize our information gain? There is some way to do it, don't get me wrong. We're going to talk about it in a moment. But that is the main question that is associated with decision trees. It's all very well and good that you have a bunch of different rules for this stuff, but if the computer isn't able to evaluate it automatically, it's kind of pointless. So we have to do some sort of counting and calculation to figure that out. One option is actually, let me see the next slide. Scroll down. Okay, sure. Yeah, so one option is to calculate a threshold. So in the case of like continuous data, where someone has a GPA that is between like 0 and 4 with a bunch of decimals in between, we can draw some lines. So we can see that like the people from 4.0 to 3.7 were accepted. So we can draw a line here and say, yeah, anyone within that GPA should probably be accepted. And we can add a rule saying if your GPA is greater than 3.7, we're going to accept you. If it's 3.5, we're going to reject you. If it's 3.4, we're going to accept you. And if it's below that, we're going to reject you. So we can decide more or less ad hoc by looking at our data where we want to split it. This can be used within our thing. If you look at the top right there again, this is an example node in our tree. So if the GPA is greater than some threshold or within some sort of range, then we're going to accept. Otherwise, we're going to reject. And we can keep going from there. There's plenty of other examples here. You could do like height or weight or whatever you want, depending on the problem. It really depends. So looking at our original table here, we can change a few things out. So good GPA, if we were to make this data non-discrete, good GPA in this case would be something like greater than 3.5. Good SAT would be greater than 1500. It doesn't particularly matter. And then suspended can be categorical. It's just a yes or no. Whether or not you're MVP on the sports team, same thing. It's just a question of drawing the lines and coming up with these rules yourself. Additionally, this is just a separate problem with decision trees as well. That's always important to mention is the concept of overfitting. Overfitting is also sometimes called fitting to the noise, because what ends up happening is your data, your model ends up just fitting to the noise of the thing. A good fit is just going to be something that follows the shape and has general shapes of the data, but is flexible for the population. You want something that follows the data, but doesn't exactly show where it is. If you look at the bottom right there, that is terribly, terribly overfitted because it has no flexibility. What we want is something that follows the shape, like at the top there. And this is a very big problem with decision trees. There's a few ways to counteract this, but a very, very common one is to just limit the depth. So every single time you go down a layer in a decision tree, you're going to be adding a new rule. So let's say you go from GPA is greater than 3.5 to had an extracurricular to wears blue shoes or something. One of those isn't really particularly useful and is just going to be a very small subset of the data. So we can counteract that by just limiting the depth of the tree. And then another very common one that's often used in conjunction is just adding multiple trees. The thinking is that basically, if you have multiple trees and each one has some amount of error, by having all of them predicting together and then based off of what all those trees predict individually, they vote on what the result should be, you're going to minimize that error because you're going to be getting an aggregate. The same thing is asking a bunch of people to guess whether or not a number is prime. You're probably going to get a pretty good answer, even if those people individually don't know and are just making gut reactions. All right. On the topic of a random forest, which is just the collection of decision trees, basically is what I said. Every tree votes on something, and the one with the majority vote is the pick. So if you go tree 1, tree 2, up to tree n, and the majority pick is class B, then the final pick is class B. And these are often a lot more robust, just because there is reduced noise from these different predictions. But yeah, that's more or less the concept of a random forest as far as I can tell. Okay, great. Oh, yeah, one moment, Kevin has a thing. Yeah, of course.
I think that, uh,
Thank you, Kevin. Okay. Yes. Before we move on to the code, does anyone have any final questions that you'd like to be on the recording? If not, we can leave out those silly people and they can wonder to themselves. So, the code that we're doing today is the top thing. I don't know whose bag that was. The code that we're doing today is the top thing. That's at tinyurl.com/sky, SCAI -DT for decision tree. And this is a QR code for a feedback form. This is just to let us know what you might need help on or what you might want to see. Oh, yes. And please fill this out after the notebook because that'll help us more. And Cohen is the one who made it, so he'll actually know what's in there. I haven't had a chance to look. But yeah, I'll wait for you guys to open up the notebook. And in the meantime, if anyone has any questions, feel free to ask. Probably hand this off to Cohen or maybe Kevin because I think they have more experience than I do, but I can do my best. Yes, yes. Make a copy.
That's okay, just to get things downloaded. Everything is already set up.
Yeah, that's the main thing. Always make a copy for this stuff. It'll actually make things run. Okay, but I think that'll more or less cover us here. So give me one moment and we'll get to it.